Okay, so our topic for this week is accelerated frames of reference. So I'm going to write that as FOR for frames of reference. Now, an inertial frame of reference is one that moves at constant speed relative to other inertial reference frames. Newton's law of inertia will apply there, and therefore objects at rest remain at rest and objects in motion tend to remain in motion. And all forces are based on real interactions between two objects. In an accelerated reference frame, though, inertia appears to be a force. This force doesn't originate from the interaction between any two objects, and is therefore sometimes called a fictitious force. So we'll go through several examples of accelerated reference frames, but the main thing is they're accelerating relative to an inertial frame. And the direction of that fictitious force will be opposite to the direction of the acceleration of the reference frame, and the magnitude of that force will just be ma. Now, in the accelerated reference frame, you can add the real forces to the fictitious force to get the net force, and then just set it equal to ma. Let's look at some examples. Here's a car, and here's fuzzy dice. Now, with the car moving at steady speed in an inertial frame with no acceleration, the dice will just hang straight down. And the forces that act on the dice will be the tension in the attached string and the weight. And those two forces just balance each other out. And there's no forces in the x direction. And that's good because there's no acceleration in the x direction. Now, let's imagine next that the car is actually accelerating. So now you've got an accelerating car. And now let's view it from the ground. Well, when you look at it from the outside, you will see that the fuzzy dice have tended to remain in place while the car and the attachment point have moved forwards. So it will adopt an angle like that. Now, if you accelerate at that steady rate, it will stay at that angle, and our force analysis will be as follows. You'll have a weight force and again a tension force. There's an angle theta here for the chord with respect to the vertical. And our force analysis is going to say in the y direction, with the y-axis being up here and the x-axis being this way, that t cos theta minus mg is the mass times the y acceleration, but there's no y acceleration, so t cos theta balances mg. In the x direction, we have t sine theta, and that just equals the mass times the x acceleration, which is just a, the acceleration of the vehicle. So that is in the inertial frame. We apply the second law in the inertial frame. But if we're actually sitting inside the car, okay, then inside the car, the road seems to be going backwards relative to us, and we don't seem to be moving, and the dice seem to move backwards. Why? Well, inside the car, there's a tension force from the string, there's the attractive gravitational force from the Earth, but there's also the fictitious force. FICT, the fictitious force, that equals ma. Now that's not a force based on any interaction, that's just the inertial effect, but in the accelerated reference frame, it acts like a force. So in the accelerated reference frame, our force equations would read, well, in the y direction, with this angle being theta, it's still t cos theta minus mg is 0. But in the x direction, you'd say we've got a forwards t sine theta, we've got a backwards ma, and an equals 0, because the dice are not moving in the accelerated reference frame. And therefore there's no acceleration, and therefore the forces should sum to 0. Let's look at another example. Here we have a person in an elevator car, and the elevator's in free fall. Now, viewed from the ground, the only force acting on the person is the mg force. There's no normal force from the floor, because they are in free fall with the car, and therefore the car cannot push upwards on them. There's the car accelerating downwards. So we would apply Newton's second law. The net force is mg. That must equal ma. So the person is just in free fall with the car. Now, viewed from inside the elevator car, the person would say, okay, there's a downwards gravitational force, and I'm not moving, so there has to be balanced forces acting on me. There is this upwards fictitious force that balances out my weight. This fictitious force exists because we're in an accelerated reference frame in the elevator. So with the y direction being downwards in this case, we're adding up the y forces here, it's going to be mg minus ma, the fictitious force is 0. So we call it fictitious because it's not based on any interaction between two objects. The gravitational force is the attraction between the person's mass and all of the earth ball. So that's based on an interaction between two objects, and it forms an action-reaction pair. This fictitious force is not based on the person interacting with any other object. It's simply because they're in an accelerated reference frame, and there is no action-reaction pair. Now, down here at the bottom, Einstein realized because the acceleration of this elevator car in effect made gravity disappear, because you feel quote-unquote weightless here, that in some way a gravity field is an equivalent to an acceleration. So there's no way to tell from the inside of this car whether you're in free fall or there's just no gravitational field. You can't tell the difference. So the two must be the same. And this is called the principle of equivalence. You can't tell the difference between a gravitational field and an acceleration. So we can just underline that. Principle of equivalence says there's no way to tell the difference between a gravitational field and an acceleration. All right, now, when we're moving in a circle, our inertial tendency to keep going in a straight line leads to an apparent outwards fictitious force known as the centrifugal force. Now, when we're moving in a circle, we know that we're actually accelerating inwards. So the direction of the fictitious force will be opposite to that. So opposite to the centripetal acceleration, i.e. outwards. How much fictitious force do we get? Well, we know the fictitious force is ma, but the acceleration when you're moving in a circle is v squared over r. So there's the fictitious force. There's a great comic here. You can go to xkcd.com and look at the Mr. Bond / centrifugal force, and there's a nice discussion between Bond and a villain. So let's look at things moving in a circle. Well, let's just label this as the inertial tendency before we leave the page here. So here's an amusement park ride, the wave swinger. Now viewed from the ground, there's a tension force in the cables, and there's a weight force on the rider. And let's once again say that this angle here is theta. Let's clean that up a bit. There we go. So once again, this is theta, this is tension. So our force equations read, once again, now in terms of our coordinate system, this is going to be the normal inwards direction. The tangential direction is the direction they're actually moving, so that's kind of coming out at us. So that's the t-hat direction. And then the binormal direction will be straight up. So there's our NTD coordinate system. So here, viewed from the ground, the binormal force is balanced because they're not moving up or down. So that's t cos theta minus mg is equal to 0. And then in the normal inwards direction, we've got t sine theta. That equals the mass times the normal inwards acceleration, which is v squared over rho, but we're moving in a circle, so it's just the same as the radius r. So there's the force equation for the wave swinger viewed from the inertial reference frame on the ground. Now, from the accelerated reference frame of being in the chair, you're accelerating because you're going around a circle. You could see the cable pulling on you, you know the earth is pulling on you. You will experience this outward fictitious force, which is called the centrifugal force, that has magnitude ma, or mv squared over r. And you will say, I'm not moving in this accelerated reference frame. I'm not moving relative to the chair, so all forces have to be balanced in the binormal direction, and in that direction inwards, it would be t sine theta minus my fictitious force, and they're balanced because there's no motion in the accelerated reference frame. Now, this fictitious force, remember, is an acceleration and therefore equivalent to a gravitational field. So one way of looking at this is we actually have an apparent gravitational field here, which is tilted. You've got your real gravity field downwards, g, but then you've also got this v squared over r. And so you get an angle to your relative gravitational field. And this is a real effect, because if you put plants on a rotating platform, they won't grow straight up. They'll instead grow on an angle. Okay? In response, they will go opposite to the apparent gravitational field. They'll be growing up. Here's a car driving around a corner. Now, viewed from the inertial reference frame on the ground, let's say the center of mass is right here. So there'll be a weight force. I'm just going to draw it up here just to keep it out of the way. So there's the mg force. And there will be a friction force inwards towards the center of the circle. Let's call that friction 1. And then the ground is going to push up on this tire, normal force 1. The ground's pushing up on this tire. And this tire is also grabbing on the road. There's force of friction 2. Now, if it's about to tip, then what's going to happen is this tire is going to tend to lift off. So that means normal 1 is going to go to 0, and friction 1 will go to 0. So if we write our equations in the y direction, and just let the y-axis be up, I guess really it should be the binormal direction. And then the normal direction should be inwards like that. And the tangent direction's coming. Well, I guess the tangent direction's going away from this. But so in the binormal direction, you've got, oh my goodness, you've got the upwards normal forces. And then you've got the downwards weights. So it would be normal 1 plus normal 2 minus mg equaling 0. But we've just said that normal 1's going to go to 0. In the normal inwards direction, you've got your two frictions that have got equal the mass times the normal acceleration, v squared over r. But again, the first friction is going to go to 0. We're also going to take moments or torques about the center of mass. So just let me put a little x there to indicate that that's the center of mass. And what you see there is, if we call this half the width of the car, and this half height of the car, so this will be w, and this will be h. It's really half width and half height. But for torques about this point, the normal force acts a distance w away, and that is going to be in the clockwise direction. So you've got normal force 2 acting a distance w away from the pivot, and then friction 2 acts a distance h away from the pivot. Let me just move this picture out of the way here. And then if the car is about to tip but hasn't tipped yet, those torques also sum to 0. Well, now let's view that action from the inside of this about to tip vehicle. So there's still a gravitational force. Okay, we've said we're about to tip, so we'll just draw a normal force at this wheel and a friction force at that wheel. Inside the car going around the corner, there is a fictitious force, and this car is clearly circling this way, so outside would be going this way for us. And that fictitious force is the mass times the acceleration, v squared over r. So when we sum forces in the binormal direction, normal force and weight just cancel out like they did earlier. In the normal direction, we would say that there's a balance between the friction force and the mv squared over r force. It's supposed to be subtraction. And then when we sum the torques about the center of mass, we again get a friction force acting a distance h away from the pivot, and this normal force acting a distance w away from the pivot. They cancel out. Now, because the friction force equals the mv squared over r, you can see here that the tipping torque comes from the mv squared over r force. So the torque of the mv squared over r tips the car in the accelerated reference frame. So you see the centrifugal force tipping the car, making it rotate about this point. Now, really, when you're viewed from the ground, what actually happens from your point of view is different. What you see there is you see the large friction force on the tires causing the car to rotate in this direction, and that's what tips it over. So in the accelerated reference frame, you say, hey, mv squared over r acting at the center of mass is making me rotate this way. In the inertial frame of reference, you say the large force of friction on the tires is creating a torque about the center of mass in that direction. Both of these descriptions are valid. Now, we're going to be interested in rotating reference frames. And we've been talking about this centrifugal force, which we can write, of course, as mv squared over r. And it can also be written as m omega squared r, because omega is v over r, is the rate of change of theta. There's another one, though, that's called the Coriolis effect. And it's given by a vector cross product. So in this occurs when you have an object that's moving. So you've got a mass m, which is moving in the accelerated reference frame. So it's got a velocity in that reference frame. And omega is the rotation of this rotating reference frame. Now, the omega vector, as a vector, it's perpendicular to the plane of rotation in the right-hand sense. So that if you had a disk that was spinning like this, then you would curl your fingers of your right hand in the direction of that rotation, and the omega vector would be pointing up like this. Now, remember with cross products that the answer ends up being perpendicular, direction ends up being perpendicular to both of them, given by a right-hand rule. So we're going to take v this way, and then we're going to curl the fingers of our right hand in the direction of the omega. And if you do that, your thumb would point out of the page. So the force is perpendicular to the plane determined by v and omega, and in this case, it's out of the page perpendicular. Now, if we go back to the previous examples where we looked at things going in a circle, the object was at rest in the rotating frame. So there was only the centrifugal force to worry about. This is the wave swinger in the tipping car problem. But now let's start to consider objects that are actually moving in the reference frame. Let's consider the simplest case, the rotating merry-go-round. Now, if the merry-go-round is spinning in this direction, then if you follow that rotation with the fingers of your right hand, you find that the omega vector is pointing straight up like this. Now let's imagine that you walk outwards along a radial line, so your velocity vector points like that. So that's sort of an angle view. In top view, you'd say, okay, so this is the angular displacement. The omega vector is coming straight out at me, and the velocity vector is just going towards the rim of the circle. Now, if you do v cross omega, fingers of your right hand in the direction of v, and then curl towards the omega, which is out of the page, you find a force that's directed this way. That is the Coriolis force. And it happens when you're moving in a rotating reference frame. So, it's perpendicular to both v and omega in a right-hand sense. Now, in this case, it ends up being opposite to the direction of rotation. And it's always going to be, because it's perpendicular to v, that the Coriolis force is going to deflect you sideways. Now, it's going to remain perpendicular to v and omega, and so as a result, it's going to tend to turn us into a circle. So, if we started off moving this way, with omega coming out of the page, we showed that the force was in this direction. Now that means that a little later we're not going to be here. Instead, we're going to have been deflected sideways by the Coriolis force. It also means that our velocity is not going to be straight up. It's going to have been deflected somewhat by the Coriolis force again. So we're now here, we're going in this direction. The speed hasn't changed because the force is perpendicular to the velocity. If you do the right-hand rule again, you find that the force, again perpendicular to the velocity, is now like this. So we repeat again. A little bit later, you're not here, you've been deflected by the Coriolis force. Your velocity is not parallel to this one, it's been turned a bit more by the Coriolis force. Then you do the right-hand rule and you say now the Coriolis force is in this direction. So what you get out of that is a circular arc. But of course, it's not that simple because really there is the centrifugal force as well. And the centrifugal force is going to act outwards. Now, it's going to speed the object up, so the speed isn't constant as we saw here. It would be constant if we had only the Coriolis force. Because the force being perpendicular to speed doesn't change the speed. It doesn't do any work. So if we include then the centrifugal force, here's what happens. Okay, so your speed is like this. Our Coriolis force is in this direction, sideways. That's the F Coriolis. The centrifugal force is outwards. So, as a result, we're going to, instead of, say, here, if we'd ended up there with just the Coriolis force, we're going to be deflected a little bit this way. So if this was our circular arc earlier, because of the centrifugal force, we're actually a little bit further in the y direction than we would have been otherwise. Now, a little bit later then, our velocity will have increased. We're now going actually a bit faster because the centrifugal force causes us to pick up speed. The Coriolis force is still perpendicular to velocity, and the centrifugal force is directly outwards. Now, that's no longer parallel to the direction that it's moving. The centrifugal force is now about like this. So once again, it gets deflected by both of these, and a little bit later, say maybe it's here, and it's now heading in, say, this direction here. There'll be a Coriolis force perpendicular to the direction of velocity, and there'll be a centrifugal force acting outwards directly along a radial line. The result of those two gives you the acceleration, and that gives you the change in velocity. It's a little bit complicated. Oops, let's undo that if I can. Yes, I can. That's good. It's a little bit complicated, and there's a couple of nice simulations for you to watch that do a pretty good job. So you can just fire these up, watch these for a bit, and then that will do it for this pre-lesson. I don't know why those aren't working. I did make them into links. Let's try that. It's supposed to just open up YouTube. There it is.
Coriolis Effect. An object in motion appears to be deflected from its course.
Anyway, you can watch these on your own. There's 2 of them there. And that's it for our introduction to accelerated reference frames. We'll pick up at that point when we meet in class.